Hello, welcome back. Today we're going to be looking at least squares fitting. So we're going to imagine that we've collected some data in the lab and I've plotted it here. So for the moment we're going to keep everything very general. I've just labelled the axes X and Y, and we're going to try and fit a straight line to this data. So if we look at the data, we can see it looks as though it's feasible to fit a straight line to this data, and for the moment we're just going to by hand draw a straight line through the data that's as good as we think we can get it by eye. So if we do this, we can draw this straight line through our data, and this straight line is going to have the equation y equals mx plus c, where m is the slope of the line and c is the intercept. So how good is this line as a fit to our data? Well, if we look at it, we can see that qualitatively we've got some of the data points are above the line and some of them are below the line, and those are roughly equal in number, so it's probably a reasonably good fit. But we actually want to be able to quantify that. So how can we tell definitively how good this line is as a fit to our data? Well, what we're going to do to find out, we're going to draw a straight line between each of our data points and the straight line, and these values are known as the residuals, and we can tell the length of each of these lines is given by the distance between the data point, which has coordinates xi, yi, and the line itself, which is y equals mx plus c. So we can actually measure the length of each of these lines. One thing you might think about doing is to say, well, we can use these as a measure of how good the straight line fit is, because we can add all of these up and try and make it as small as possible, and that will be a good measure of our straight line. But you should be able to see immediately there's a problem with that approach, because if we do that, some of these delta y are going to be positive and some of them are going to be negative, depending on whether the data point is above or below the line. So instead of that, what we're going to do is look at the square of each of the residuals. So just to visualise this a bit better, I'm going to draw the squares on, so now you can see exactly what we mean by the square. And this is always going to be a positive quantity, so when we add these up, we're always going to end up with a positive number, and we can use this as the quantity that we want to minimise to measure how good our straight line fit is. So for example, we can add up the sum of the squares of the residuals to give us our quantity s. So we can minimise this in order to calculate the best possible slope and intercept through our data. So we've got two quantities that we want to minimise with respect to, which are m, the slope, and c, the intercept. So this gives us two simultaneous equations, which we have here, and when we solve these for m and c, we end up with these expressions here, which are the equations that we need to solve to find our m and c. To help you see this a bit more easily, I've written a code so you can visualise this and play around with it. So what I've got here is a code where I've plotted the data, which are the points in red, and I've calculated the best straight line fit through these data points using the method we've just discussed, which is the line in green. And I've also drawn on the squares of the residuals in blue. So that you can visualise it, we can change the value of the slope and the intercept, and it will automatically recalculate the squares of the residuals. So for example, if I went to make the slope a bit steeper, you can see how the squares move and they increase in size. Obviously, it's clear now that this is not a very good straight line fit here. It doesn't go through any of the data points, and you can see the sum of the squares here that I've calculated is now very large. It's 588. We can also change the intercept. By changing the intercept, we can reduce the sum of the squares, or we can make it even bigger if we want an even worse fit through our data. But you should be able to see, as we change the slope in either direction, the squares are smallest when the line is best, which is around here. I'm trying to get back to the original position. So hopefully by using this code you'll be able to visualise exactly where the squares in least squares fitting come from, and be able to see more clearly what we do when we're minimising the total sum of the squares. So I hope you find that useful.